Now we reach the culmination of our journey through information retrieval. We began with the foundational statistical models TF-IDF, BM25, which taught us to think about documents as bag of words and to rank them based on term statistics. We then moved into the neural era with word and sentence embeddings like word2vec, GloVe, which helped us to capture semantic meanings and address vocabulary mismatch problem. This was a significant step beyond keyword matching. Recently, the advent of transformers and BERTs marked another leap, which introduces deep contextual understanding. These models allowed us to understand that the word bank could mean very different thing in different contexts. Now we stand at the latest frontier, the era of large language models. These models are not just an incremental improvement, they represent a fundamental shift in capability, blending deep understanding with generative power to redefine what's possible in search. So what exactly are these large language models, or in short, popularly known as LLMs? A detailed discussion on how LLMs work is beyond the scope of this course. Here I will briefly introduce LLMs, focusing more on comparing it with other tools that we have already discussed. The basic architecture of large language model is primarily based on transformer model, which uses self-attention mechanism to process input sequence efficiently. Key components include an input embedding layer, converting the text into numerical vectors, then multiple transformer layers with self-attention and feed-forward networks, and one output layer to generate predictions like the next word. LLMs rely on various parameters and hyperparameters such as weights, biases, temperature, and activation functions to function correctly. Each component is crucial in the model's data processing and response generation capabilities. Now, while BERT with its hundreds of millions of parameters was a breakthrough, LLMs operate on a different order of magnitude with billions or even trillions of parameters. They are trained on trillions of tokens of text, absorbing a significant portion of the knowledge in the digital world. Now, architecturally, many popular large language models like GPT, Llama use a decoder-only transformer structure, which optimizes which are actually optimized for generating coherent text sequence. This massive scale actually unlocks capabilities that are directly transformative for information retrieval. And together with that, it can also be applied for natural language understanding, fluent text generation, and multi-step reasoning, and the ability to follow complex instructions. These will be helpful, can be helpful if we apply them for efficient information retrieval. Let's break down these capabilities in the specific context of information retrieval. On one hand, we have natural language understanding and reasoning, and of course inference. This means an LLM can parse a complex conversational query like find me a paper about using, let's say, neural networks for climate modeling, or let's say how the Second World War started. This is a query. A traditional information retrieval system would be comparing the term overlap between the conversation-like query with the document, but will never be able to understand the natural intent. But LLM can recognize the user's intent, infer context, and perform logical deduction to understand what is being asked. On the other hand, we have generation capabilities and instruction following. This capability is beyond imagination for an IR system. This capability of LLM actually allows the system not just to retrieve but to act. It can reformulate a poor query, summarize a set of documents into a concise answer, or execute a multi-step retrieval based on a single complex instruction. This moves us from basic retrieval system to an information access system, a basic information retrieval system was only working based on the overlap or meaning understanding, but this generation capability incorporated into that system is actually making the system much more robust. Now, these capabilities translate into several concrete applications across the entire information retrieval pipeline, which we will briefly mention. We can use LLM to deeply understand and enhance the user's query, that by query understanding. We can process and enrich documents while doing the document processing before they are even indexed. We can even improve the core retrieval and re-ranking with more semantic and reasoning powered approaches incorporated by LLMs. And finally, we can move beyond returning a list of links to directly generating the answer with some explanations. So this capability was the unique thing that was never been able to, we can never actually achieve that using the simple information retrieval approaches. But the capability of LLM to generate some answer, and if we incorporate that into the information retrieval system, that will be directly generating the answer, not just giving some 10 blue links. Let's start at the beginning of the pipeline, that is, understanding the query. LLMs excel at transforming a user's query, which might be vague in nature most of the times, into something a retrieval system can handle more effectively. So for that first part, the query reformulation, an LLM can take a query like best phone 2024, which has kind of a vagueness in its inherent nature, and it can expand it into a more descriptive one that is likely to match relevant document language. For query expansion, it can generate a list of semantically related terms going far beyond what simple embedding lookups might actually provide. Furthermore, LLMs can perform sophisticated intent classification as well, determining if a user wants to navigate, find information, or make a transaction. They can even break a complex question into multiple questions such that every subqueries can be effectively answered with some effective search strategies. Just as we can enhance the queries, we can use LLMs to enhance the document as well. This is a powerful way to enrich our index and improve retrieval quality. We can use LLMs for automatic document summarization, which will be creating a short abstract that can be searched more efficiently or displayed as the results. They can actually generate rich metadata as well, like keywords, topics, entities. This will be freeing us from the reliance on the human tagging. We can even use the LLMs for document enhancement, such as generating a list of frequently asked questions from a technical document, which then becomes let's say a new searchable assets. And let's say we have a multimodal collection. Multimodal means there are text document as well as, let's say, images. For those kind of multimodal collections, LLM with vision capabilities can be applied to this cross-modal understanding, which will be able to describe images and tables, making non-textual content also searchable. Now let's look at the core retrieval task itself. We have discussed dense retrieval using models like dense passage retrieval (DPR). A key limitation of these models is that they often produce static one-size-fits-all document representation or document embeddings. LLMs offer a solution here. We can now create a query-aware embedding, where the document's vector representation is dynamically influenced by the specific query, the submitted query to the system. We can also use an instruction-tuned embedding or instruction-tuned embedders, which are LLMs fine-tuned with commands like represent this document for retrieval. This actually significantly outperforms generic embeddings. Models like Google's GTR or Microsoft's E5 are examples of this new generation of retrieval specific embedders that leverage the power of LLMs to create a much more powerful dense representation. After we have a candidate set of documents from a first phase retrieval, we enter the re-ranking stage. Traditional neural re-rankers, including BERT, typically provide a simple relevance score. However, LLM-powered re-ranking is far more sophisticated. It has so many better capabilities. It can actually generate an explanation for why a document is relevant. It can perform also multi-aspect evaluation, judging a document on dimensions like credibility, timeliness, and depth. It can also comparatively analyze document pairs, and even it can use chain of thought reasonings to work through a complex relevance decision step by step. Now, this next concept is perhaps the most radical departure from traditional information retrieval. This is called the generative retrieval. What if instead of building an index and searching through it, we trained a single LLM to directly generate the identifiers of relevant documents when given a query? This is the key idea behind models like differential search index or SIL. In this paradigm, the entire retrieval process is condensed into a single model. The model itself becomes the index, and this is actually a true paradigm shift, as you can understand. It blurs the line between retrieval and the generation, and it kind of opens up a fascinating new research direction where the retrieval and the generation will be happening together. Now we come to the architecture that has become one of the most sought after solution in many tasks involving search. That is RAG, or Retrieval Augmented Generation. RAG elegantly combines everything we have learned. It's a three-step process. Step 1, Step 2, and Step 3. First, we retrieve a set of relevant documents using any of the traditional or neural IR techniques. As we have mentioned, classic BM25 is very much applied in this step. Then we augment the LLM's context by feeding these retrieved documents in the first step along with the actual original query. And third, the LLM generates a final grounded answer based on the provided evidence. This is actually a hybrid approach, as we can understand, that applies the strength of both dedicated retrieval in the first stage and the powerful generative model in the third stage. So why has RAG become so dominant? Because it directly addresses the core weakness of pure LLM. LLMs on their own can hallucinate, can be stuck with their training data cutoff, and cannot attribute their sources. On the other hand, RAG actually grounds the LLM in factual and up-to-date information retrieved from some trusted corpus or trusted sources. This drastically improves the factual accuracy, allows for attribution, which is citing the source, reduces hallucination, and makes it easy to adapt the system to any specialized domains. This makes RAG perfect for enterprise search, technical support chatbots, and any question answering systems where accuracy and verifiability are very much critical. Of course, a RAG system has its own failure modes as well. What if the initial retrieval is very poor? What if the context is too long? So to address this, the field has rapidly developed a suite of advanced RAG techniques. We can use a query transformation to improve the initial query before retrieval. We can optimize the retrieval to include, let's say, hybrid search. We can also manage the context window through, let's say, compression and smart selection. And let's say we can enhance the generation step to include citation and confidence scores. This turns a simple RAG pipeline into a robust production grade system after including these advanced ragging techniques. LLMs are not just transforming how we build information retrieval systems. They are also changing how we evaluate them. Remember, in order to evaluate a system, a traditional IR system, we need three things. Number one is a collection of documents. Number two is a set of queries. And three is the relevance judgment. In this third step, we rely on human judged relevance levels, right? Which is expensive and slow. Now we can use an LLM as an automated judge to judge this document given the query and the document pair. This LLM as a judge approach is reference free. That is, it does not need a pre-written ground truth answer. It can evaluate responses across multiple dimensions like relevance, coherence, the quality, the depth, and crucially, it can provide natural language explanation. Why is it marking a document as relevant? Why is it marking another document as non-relevant given one query? This enables rapid and scalable evaluation of our retrieval and generation system. Taking this a step further, we arrive at agentic retrieval systems. Here, the LLM acts as an autonomous agent that plans and executes complex search tasks. It can break a difficult query into multi-step reasoning process. It can use tools like, let's say, calling a search engine API, querying a database, or even using a calculator. Then it can actually self-correct, refining its query based on initial result. And finally, it can synthesize the information from multiple sources into a comprehensive answer. With all these potentials of LLMs, it's vital that we at least mention the significant challenges with applying LLMs in our system. Technically, LLMs are computationally very much expensive. Also, they are slow at inference. The problem of hallucination can be reduced using RAG, but they cannot be eliminated. Still, till now, the researchers were unable to eliminate the hallucinations altogether. Also, there is the context limit. We cannot provide a very long text to LLMs. Now, from a retrieval perspective, the entire RAG systems fail if the initial retrieval is actually a poor one. Also, noisy documents can mislead the entire LLM generator. And we must be aware of the biases present in both retrieval as well as the generator. We should remove or avoid biases as much as possible. Practically deploying a system involving LLMs require complex infrastructure, which will again be expensive. And we also face the ethical questions about copyright, attributions, as well as the fairness of the system. Now, despite these challenges, LLM-powered information retrieval systems is already here in production systems. Commercial search engines like Google, Microsoft's Bing are already deeply integrating LLMs into their core model. New entrants in the search domain such as Perplexity or U.com are building entirely AI native or AI assisted search interfaces. In the enterprise, platforms like Elasticsearch is adding LLM capabilities, and a vibrant open source ecosystem has emerged with frameworks like LangChain, Llama Index, and so on. This makes it easier for us to build these sophisticated pipelines. This is not only enabling the industry, but they are also enabling the academic practitioners like us to do research involving LLMs. So where exactly this research on LLM powered IR is actually heading towards? We see several key research directions. Architecturally, we are moving towards end-to-end training of retrieval as well as the generation components. There is a strong push in efficiency, making the model smaller and faster without sacrificing the capabilities, such that they can actually run on smaller devices like our smartphones. We are also working towards more advanced reasoning capabilities and tackling the critical ethical and societal implications of these powerful systems. If we can proceed with the development in the right direction, with the right intent, the future of IR is expected to be more integrated, more efficient, and more responsible. To summarize, LLMs are revolutionizing information retrieval by transforming it from simple retrieval task into an intelligent information access process. The RAG architecture has emerged as a powerful hybrid tool combining the best of traditional information retrieval with generative AI. We have multiple application points across the pipeline, and agentic systems are opening up new possibilities for complex tasks. Now, while significant practical challenges around cost, latency, hallucination, evaluation is still there, this research domain still remains an intensely active and exciting area for IR and AI practitioners. The key takeaway of this lecture is that LLMs are not actually replacing traditional information retrieval. They are actually enhancing and complementing the traditional information retrieval, creating more intelligent and conversational tools for improving the search experience of the users. So if we apply LLMs in all the components in the entire pipeline of IR, how will it look like? In that case, we will begin with an LLM powered query processing. Then we will use a hybrid retrieval to get a broad set of candidates. Then we will apply a sophisticated LLM powered reranking to bring the best at the top. After that, we will be applying the LLM for the final generation, the final answer generation. Finally, we can employ an LLM based evaluation to continuously monitor and improve the system. And with this, we complete our journey. We started this course with the basics, bag of words, TF-IDF, BM25 language model. Then we have concentrated on addressing the vocabulary mismatch problem with some vectorized and statistical ways. We have learned the use of PyLucin, which is an industry standard retrieval system. Using PyLucin, we have indexed, searched various types of textual data, including in English as well as in Indian languages. We then learned how word embeddings and semantic search could capture meanings. We advanced to deep contextual understanding of transformers and BERT. And now we end at the frontier with large language models, generative retrieval, and RAG systems. It has been a journey from counting words by statistics to understanding intent and generating knowledges. Thank you.